Hello and welcome back. In our last video, we looked at using adjusted R-squared to determine the best model. However, there are other methods available for choosing the best model, and these include ideas such as the Press statistic, CP statistic, elimination methods, and they also include lasso and Bayesian model averaging. However, the latter two will not be discussed in this video. Now, with Press statistic, this involves removing each observation beginning with the first, fitting the model with the remaining observations, estimating the removed value using this fitted model, computing the model residuals, and then repeating the above steps with the remaining observations until all observations have been exhausted. Then comparing the residuals. And the model with the smallest Press statistic is going to be selected as the best model. So the model with the smallest residual is selected as the best model. However, this is time consuming. Another method is the Mallow CP method. This is another way to choose a best model from several choices. So for a given regression problem, one computes a CP statistic for every regression equation that is fit. The preferred CP value is the smallest with CP near P, where P represents the parameters in the model that include all P parameters and their subsets, along with the model which only includes the intercept. Now, Mallow CP is calculated as the sum of squares residual for the Pth model. In other words, the Pth residual sum of squares divided by the sum of squares error from the regression equation with the largest number of independent variables minus n minus 2p, where p is the number of model parameters and n is the number of observations. But CP statistic involves fitting each of the 2 to the k models. Remember, in multiple linear regression, there are k parameters. If k happens to be 5, then that means there are 2 to the 5th, that's 32 models, plus the model with only the intercept. This is also time consuming. And so Press and CP both require running multiple models. Elimination methods, however, these are another model selection method, and it involves either adding or eliminating variables to determine the best model. And there are 3 ways to do this. In the forward elimination method, one begins with only the intercept included in the model. So we have y equals beta 0 plus epsilon, and find the best fitting regression model by adding one variable at a time. However, once a variable has been added to the model, it cannot be eliminated. In the backward elimination method, one begins with the full model. So we have y equals beta 0 plus the sum of beta I xi plus epsilon, and then find the best fitting regression model by eliminating one variable at a time. However, once a variable has been eliminated, it cannot re-enter. The third method is called stepwise. And with the stepwise method, this procedure is the same as the forward method. However, variables may enter or be eliminated. So a variable which entered or was eliminated at an earlier stage may be included in the final model. Stepwise is programmed in R, and we're going to use this as our example. Now we're going back to the Bears data set, and remember we had weight, sex, head length, head width, neck size, body length, and chest width. And in an earlier video, we saw that sex was included in the model. And so we had sex by head length, sex by head width, sex by neck size, sex by body length, and sex by chest width. And so we're going to call this our YLM. And so this is our full model, including sex. And so what we want to do when we do our stepwise elimination method, we're going to use the step function in R. We're going to plug in our linear model, and we're going to put in direction equals backwards. And when we run this, what we see is that we get the following output. Now you'll notice that we have this AIC value that we'll discuss in a minute, but notice these are our coefficients. So these are the values that our stepwise method is saying we need in the model. Our intercept, our sex, our head length, our neck size, our chest width, our sex by head length, sex by neck size, and sex by chest width. We're going to look at a summary of this model and see what we get. Well, if we take a look, we see first we have a significant p-value for our F statistic. That means we have model predictability. We have an adjusted R-squared of 0.9091. And notice, in this model, each of these looks to be significant at an alpha of 0.05, except for sex by chest width. But this needs to be included because this is the best model chosen. And so our best model here, that I'm calling YLM best, is the model that we just looked at. But again, we've got sex in our model. And so, what does that mean? Well, it means that we need to account for male or female. What that means is that if we look at being a male, our intercept is now negative 122.233 minus 53.871. And then we have negative 5.603 minus 7.952 for our head length. We have 3.114 plus 11.474 by chest size, and 8.811 minus 1.960 times chest width. However, if we're a female, now our sex goes to 0, and so sex by head length, sex by neck size, sex by chest width also go to 0. And so for a female, our model is negative 122.233 minus 5.603 times head length, plus 3.114 times neck size, plus 8.811 times chest width. Let's go back to our stepwise method. Elimination methods are conducted sequentially. And while we could do a partial F-test to determine the best model, we're going to rely on a minimization criterion. And so our goal is to choose the model which minimizes our mean square error. And there are two methods that can be used. In our R output, what we saw was an AIC. This is Akaike's information criterion. However, there's also a BIC, Bayesian information criterion, which can be used. But R gives us AIC. So what is AIC? Well, the goal behind AIC is to choose the model with the minimum mean square error. However, because there are 2 to the k possible models, AIC selects the model by penalizing for the number of k parameters used in each model. And so AIC is negative 2 times the mean square error plus 2 times the number of parameters included in model I. And the model with minimum AIC value is considered the best model. So, if we include each of these values, notice our AIC for all of these is right here. With BIC, the goal behind BIC is similar to AIC. The goal is to choose the model with the minimum mean square error. However, BIC selects the model by penalizing for the number of k parameters used in each model, with an additional penalty assigned for the number of n observations. And so BIC is calculated as negative 2 times the mean square error plus 2 times k. But that is negative 2 times sigma squared plus k times log n. So sigma squared is the mean square error for model I, k the number of parameters in the model, n the number of available observations. And we will consider BIC as minimum BIC as the best model. Which one is best, though? Because either AIC or BIC can be used as a model selection method. But regardless of the one you choose, you need to pick one and stick with it. Once you've determined the best model, you can then do your global F-test to make sure you have predictive capability. You must keep all variables chosen using the elimination methods, even if some of these are insignificant. Likewise, if a significant interaction exists, you must keep the individual variables in the interaction, even if one or both individual variables are insignificant. That's it for this video. In the next video, we will look at analyzing the results. See you then.